Okay, so on.
Can I use that?
Sure.
Yeah,
Both? Excellent. So I'll move here so it's focused to you.
Welcome, everybody. So, a slight difference in how we normally hook up. If you do want food or drink to be ordered, walk around to the platform bar and put your order in. If everyone has gotten it already who wants to, you can get started. I don't see anyone standing up to rush over. All right, so let's get started. I'm Kathy Abella. I'm a physics professor at Mount Holyoke College. How many of you are new to ScienceCafe Cafe? Oh, we have some new people. Excellent. Welcome. Thank you for joining us. ScienceCafe Cafe is something that is unique in the communication of science by scientists, in that it is the persons themselves who, science mathematician, I don't know, some mathematicians get upset when I just say scientists, scientists and mathematicians who are doing the work themselves, who are researchers, who come to talk to an audience that has no background. And rather than what you see when you watch a documentary or go to a museum exhibit, this is meant to be interactive, to ask you questions, to think about, how does this person answer this type of question, or what do you really mean by this? And so we encourage questions. We encourage questions to the point of prizes for best questions. And we see there's fewer kids in this audience, so there are going to be many lucky adults walking home with this math toy. We have several of you. And this is also what we have for the raffle ticket. So please make sure you have a raffle ticket. It is how we count how many of you are here and how we then tell our sponsors how successful we are. So we'll raffle off some of these and we'll give out some prizes for best questions. So ScienceCafe Cafe, we encourage the questions. We want this to be a dialogue, a conversation. If you have already asked 2 questions, then maybe whisper your 3rd question to your neighbor and get your neighbors to ask that question, because we don't want any one voice dominating the conversation. And there will be times when Steve is going to say, I'm going to get to that later, or hold your questions, I want to move forward. So don't be offended if your question gets put aside for a while, and afterwards you can also come up and talk with our speakers. So ScienceCafe Cafe cannot happen without a lot of people putting effort in and some people putting money in. So I want to thank Barbara, who is still out there. We greeted you at the door, so thank you, Barbara. She didn't hear me, so that's good. Sarah Byrne is the academic coordinator in the physics department at Mount Holyoke, and most of the heavy lifting is done by her to organize everything and get stuff going, so that I just call up the scientists I know and try to persuade them to come and give talks in this venue, and then show up for the days of the event. Funding is coming mostly from the National Science Foundation through a grant of my own and through the Center for Integrated Quantum Materials that is based out of Harvard and MIT. And one of our speakers later, who is a quantum mechanic who designs devices, quantum devices, will be speaking in March, I believe. And community-based learning at Mount Holyoke, which is an organization, a part of Mount Holyoke that strives to create mutually beneficial relationships between the academic classrooms and the college and the community. So what we have for our next month's event is Gary Feldberg. Have any of you been to his talk so far? He's been a regular. He has told us about the early universe. He's told us about dark matter and the Higgs boson. He is a crowd pleaser. He's excellent at communicating with people of all backgrounds and all ages. So he will be October 23rd to talk about gravitational waves, which if you did go to his early universe talk, he kind of gave a teaser at the end. They've just been discovered, but we still spend our time talking about the early universe. We are fortunate to be in an area that has quite a few science events for the public, including the Organismic and Evolutionary Biology Cafe, the OEB Cafe. And their lineup for the year, starting on September 8th, that happened already then, and October 13th, unprotected pollination, how pollinators transmit plant diseases, and then moving on to how and why we walk upright, and then surfing and heat waves and challenges faced by migratory and desert birds. So OEB Cafe, they have a website and they're on a mailing list if you're curious about any of those. Now, there might be overlap between this audience and those who came to Ben Bomber's talk on sabermetrics last year. No, maybe not. I would say, okay, yes, some. Because these are the 2 math, we've had 3 math talks in the last 4 years, so finding math topics has been interesting. So one was on baseball statistics, sabermetrics, and Ben Bomber did a fantastic job, and he is introducing Moneyball at Amherst Cinema. So if you want to go watch Moneyball with an introduction by Ben Bomber, that will be Wednesday, September 28th. He is a professor of mathematics at Williams College. And Steve, I met Steve actually when we were both, well, I was not yet an undergraduate.
Yeah, I was going to say a little bit, yes. You were, yes.
So I met Steve quite a while ago. And he is now a professor at Williams College, and he will be talking about Benford's law. So please welcome Steve.
Okay, thank you. So I was actually a visitor at both Smith and Mount Holyoke a couple of years ago, and it's always nice to be back in this part of the area. The talk is being recorded, so if anybody wants to see this again later or pass this on to a friend, happy to provide the link to Kathy who can share that. Eventually my email address will also be up here, and if anybody has further questions or wants to talk about this further, I'll be here after the talk today and would love to get additional questions. Okay, so can math detect fraud? So the natural behavior of numbers. So when I was a very young postdoc, oh, can everybody hear? Not, was that a, okay. Okay, can people hear now? Okay. Question already?
Well, if you just slow down your talking speed a little bit.
I will try. I'm a native Bostonian, so it is hard, but I will try to slow down a little bit.
I always tell my students the best way to slow me down is to ask questions. So they very quickly figure that out, and they're like, ooh, but I don't know. Okay, I have a question.
Okay, so many years ago I was a young postdoc and I got a very strange email. It began, "Greetings, my name is David Kelly. I'm a senior criminal investigator at the Internal Revenue Service." And that was about all I did for the next 5 minutes and just going, oh my God. And then eventually I read the next line, which was, "I just read with interest your paper in Acta Arithmetica." And I was, such a young professor that the fact that anybody would read any of my papers with interest, I was, sure. And so I started chatting with people at the Internal Revenue Service. And so it turns out that some of the mathematics I do has applications to detecting things such as tax fraud. And so what I want to talk to you tonight is about how some mathematics, a lot of which you've already seen, can be used for either good or for ill, depending on your desires. Since this is being recorded, I will of course say my desire is for good and to catch fraud. But if any of you have other suggestions on how to use this, I'm happy to chat off the record. All right, so here is a motivating question. For a nice data set, so I'm a pure mathematician most of the day, so for me, Fibonacci numbers would be a nice data set. But other things, stock prices if you want to make money, street addresses of the people in the audience. A good question you could ask is, what % of the time is the first digit of your number a 1? So it's 2016 last time I checked, the first digit of that is 2. So whenever I ask questions, it's open to anybody in the audience who has not already read papers on Benford's law and is a plant. Okay? So I want people who haven't seen this before. If you had to guess, what fraction of numbers would you say start with a 1 as their first digit? 1/9. So unfortunately, you're much smarter than most people. Most people would shout out 1/10. Right? And they would say 10%. And then you would correct to 1/9. Because you can't have your first digit as 0 unless your number is actually 0. So it's good to know that I'm in a strong audience. All right, so this is a natural plot of what we might expect. If it was all 1/10 everywhere or 1/9 everywhere, you would suspect the data is fake. There's some fluctuation, so this has a chance of being reasonable. So the actual answer is in many data sets, the probability of a first digit being 1 is about 30%. Not 11%. And you get a 9 only about 4.6% of the time. So what I want to do today is show you a little bit of where this comes from and what you can use this for. Why do we care about something like this? So here's a couple of examples. The first is, as I said, the Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13, etc., etc., etc. These numbers occur in a variety of problems. Maybe one of the math bio talks will talk about that a little bit later. Another great example is the most common iPhone passcodes. Because this is a public lecture, I will not tell you how I got that data set, but I will say, while this talk is supported by the NSF, it's nice to have friends in the NSA. Yes, nice shout out. Okay, another is this thing called Twitter. I'm a little bit old, so I don't know exactly what that is, but it seems like a lot of people do, and you can look at the number of Twitter users by follower count. That also follows this very similar law. And then in homage to my host, It's not exactly physics, but it's astrophysics, it's close. And my son still remembers you telling about the Pluto pushing the enter key. Looking at the distance of stars from Earth in light years. So why are we seeing such similar behavior in so many diverse systems? And what can we do with this knowledge? All right, so what I want to do today is I want to explain Benford's law, or it's sometimes called Benford's law of digit bias. I'm mostly going to talk about the first digits, but whatever I say here, you can generalize to more digits if you want to do a little bit more algebra. I'm assuming this is after 6 o'clock. Nobody wants to do a little bit more algebra, so let's just focus on the first digits. I'll discuss a bunch of examples and applications. I will sketch the proofs. Key is the word sketch, but if anybody wants to know more, just let me know. There probably won't be time in the talk to get to open problems, but if people are interested, by all means, let me know. The first thing is a little bit of a caveat. I think this picture has already been displayed. A math test indicating fraud is not proof of fraud. Unlikely events can happen. There can be alternate reasons. So Scott Adams turns out to be a very wise, kind person. He responded to my email, and he gave me permission to use this. Your travel expenses are rejected because all of your meal costs are round numbers. You're a liar or worse. I decide what to order based on what totals to a round number after a 15% tip. That's worse. This is extremely important. The purpose of math is to flag things. It is not a proof that something bad or malicious has happened. But when you have finite resources, it tells you this might be something worth investigating. So there's a whole slew of places where this digit bias occurs. The main ones for us is going to be financial data today. And so for applications, anybody here, software programmer, computer science of sorts? So one nice application is analyzing round-off errors in computers or determining the optimal ways for computers to store numbers. This digit bias actually affects system architecture. For me, the more exciting one when I'm in general is to detect tax fraud, or if you have another bent, to commit tax fraud, and data integrity. So how do you know you can trust evidence that has been presented? How do you know the picture has not been doctored? So this is one of the great applications of something like this. All right, so let me talk a little bit about the general theory. So as I've said a couple of times, the probability of a first digit of 1 is about 30%, goes down to about 4.6% for 9. All right, so let me just explain the math that we need. So the first is this notion of modulo. So we say A equals B mod C if A minus B is an integer times C. All right, so rather than going into all the math detail, it is, what time does that clock say? Okay. So we'll use the current time on that clock, so don't worry, I will not use that to keep track of how long I need to speak tonight. So that clock is saying it's a little bit after 10 o'clock. So if it's a little bit after 10 o'clock right now, what time will it be in 5 hours? Well, actually, yeah, okay. Whoever said that, I think, should be on the list for a prize. Yes, according to that clock. Although no, because I said in 5 hours, and if that clock's not moving, there is no such thing as in 5 hours. But if we actually had a clock that worked, if the budget was increased, if the National Science Foundation supported this even further, what time would that clock show if 5 hours could pass on it? 3. So we're saying 10 plus 5 is 3. On a clock, yes. Every time we go past 12, we subtract 12 and reset. So we go 0, 1, 2, 3 all the way up to 12, 0, 1, 2, 3 all the way up to 12. So when we say A equals B mod C, it just means we subtract here, if we're doing it by 12, 17 subtracting 12 is 5. The most important clock for us is not going to be a clock with 12 hours, but the mathematician's clock just has 1 hour. And so we'll say two numbers are the same mod 1 if they have the same fractional part. Another way of looking at it is chop off the integer. So if I give you the number 4.5 and 0.5, they'll both be the same because they both end in a 0.5. The next thing is the significand or scientific notation. If I want to write a number, I can write a number as some number between 1 and 10 times 10 to a power. So if I give you 2016, I can write that as 2.016 times 10 cubed. If I gave you the number 0.02, I could write that as 2 times 10 to the negative 2. If all I care about is the leading digit, I really don't care about this k. I just care about this part over here, which will always be a number between 1 and 10. So what I'm going to have is a forget-me map. And so what I'm going to do is if I want to study digits, I just want to forget about this part. Normally mathematicians get upset if you throw away parts of numbers, so we'll have to talk a little bit about how you can do this carefully. The next thing is two numbers have the same leading digits if and only if their significance are the same. Well, this makes sense. The whole point of this 10 here is just padding zeros in the beginning or the end. So 2.016 and 2016, they both have the same leading digit of 2. One of them has a k of 3, the other has a k of 0. What I want you to get from this is just a rough sense of the mathematics we need to make this work. If you really care, there's some survey articles, you can look at it more closely at home, but just get a sense of what kind of math we need for these applications. We need some basic understanding of how to compare numbers. And the key observation is, if I look at my numbers, I'm going to take logarithms, and logarithms are a wonderful transformation. Now, most of the time, you do not want to take logarithms. If you want to talk about people's batting averages, you don't want to take a logarithm and talk about the logarithm of that. But for doing analysis of data sets, logarithms are often wonderful for illuminating the relationships. And so if we take the log of a number, the log of a product is the sum of the logs, all these rules you might remember from high school or junior high all those years ago. But the main thing is that two numbers have the same logarithms mod 1 if and only if they have the same leading digits. So you don't really have to worry too much about this. I just want you to have a sense of the level of mathematics that's needed. And just in case there are some ringers in the audience, the advanced stuff going on here is in blue in the bottom. Okay. So let's look at a data set. I do not want to risk doing a live interaction, so I chose my third favorite number, square root of pi. And what I'm doing is I'm looking at the fractional parts of n times square root of pi. So I'm looking at square root of pi, 2 square roots of pi, 3 square roots of pi, 4 square roots of pi, all the way up to 10 times square root of pi. And for each one of them, I'm chopping off the integer, and I'm seeing where is it. Well, they're going to be numbers between 0 and 1, and I just look to see how many of them were between 0 and 1/10, between 1/10 and 2/10, etc., etc., etc. And so we'll say the numbers fall evenly if all these subintervals have the same number of elements. So clearly they don't all have the same number of elements. But do you think they fall evenly? And it's a small data set. There's only 10 points. What do you think? There's a discrepancy here. I have none here and I have 2 here. How severe do you think that is with just 10 data points? Yes? Not very severe. With a small data set, you would expect some fluctuations. If I gave you a data set where everything was 1/10, you might expect I'm cooking up the books. So I actually deliberately cooked it up in the other way to find something where I had a small fluctuation. What should we do if we want to see if the fractional parts of square root of pi fall evenly? Rather than looking at the first 10, what should we look at? First, oh, come on, don't be kind to my computer. I just went up to the first 100. Now there's a little bit more fluctuation. First 1,000. And then for those of you who have really good vision or in the front row, you might be able to see some very small fluctuations. So if you look at a number like square root of pi, if you look at just the fractional parts of root pi, 2 root pi, 3 root pi, 4 root pi, it seems like those are falling evenly. They're not clustering in any part of the interval. And this is going to be a key way to try to get a sense of what's going on and how we can use this to either detect or commit fraud. So the next slide requires a little bit of knowledge of logarithms. So we've already talked about writing our numbers in scientific notation and then just throwing away the powers of 10. So for 2016, I'm going to write it as 2.016 times 10 cubed. And so because I'm writing like that, my numbers fall between 1 and 10. I love logarithms. If I had a function I could choose to do to a number, I would choose to take the logarithm. The log of 1 is 0. The log of 10 base 10 is 1. So when I take the logarithms, I convert my data set from running from 1 to 10 to run from 0 to 1. And now here's the interesting thing. Benford's law of digit bias, where we have about 30% of the time the first digit is a 1, there is no bias. The bias is because of how we're looking at numbers. If we do this logarithmic change, the bias vanishes. And now what happens is if we have a data set that falls evenly over here, evenly under the logarithm, it turns out that corresponds to being Benford in the original setting. So let's say I fall about 30% of the time between 1 and 2. On here, that goes from 0 to 0.3. And that's really what's going on, is the log of d plus 1 minus the log of d. This is telling me how often I'm between these. Now, again, if you're looking at something like Major League batting averages, you're not going to take the logarithms. This is a data set that's clustered. I don't really expect there to be much fluctuation. So who are my baseball fans? Oh my God. I mean, the Red Sox are doing well this year. This is a good year to be a Red Sox fan. Okay. For those of you who know baseball, what would you expect the leading digit of a batter's batting average to be? 3? Oh, I'd love them to be 3s. 2. Occasionally a 3, very rarely a 4, and you expect the batting average to start with a 1. Sometimes, and what happens if your batting average starts with 1? You go down to AAA or lower. So there's going to be a huge clustering of batting averages between 2s and a small number of 3s. So you wouldn't expect much of a distribution, much of a spread in that case. All right, let me look at powers of 2. So powers of 2 is not too bad to go 1, 2, 4, 8, 16. And let's look and see, does this have this digit bias? The numbers get pretty big pretty fast. I'm not even going to try to read how large that number is. So I'm only going to show the first 30 numbers on the screen, but I had my computer calculate the first 60. So as I'm doing this stuff, I want you to imagine that you work for the Internal Revenue Service, and your job is to detect, do you think somebody is creating fraud? We'll talk later about whether or not it's good or bad that the Internal Revenue Service has finite resources. Around April 15, I think most of us feel that it's good that they have finite resources. Do you think that this data is suspicious? If this data is supposed to satisfy Benford's law, would you say, I think something is going on here, we should spend time and audit the powers of 2, as strange as that sounds to say. Do you think these numbers look Benford, or do you think some of the numbers look bad? And if a number looks bad, which number do you think is the most alarming? Nine. I mean, I would say 1 is doing a great job, and I would say 9 is extremely bad. Some people incorrectly argue for 8. They're wrong. The reason I think 9 is worse is if you look at the correct value of 0.046, percentage-wise, this is much further from that than that is from that. So I think 9 is a little bit worse. But we only have 60 events. So maybe the powers of 2 are Benford. And maybe if we did this much longer, much further, it would start looking like 4.6%. This is the problem the Internal Revenue Service has when they're trying to decide, has someone committed fraud? They don't have as large of a data set as they might like. Okay, so I've got a couple of computer scientists here. Who are my computer scientist people? Okay, how many megabytes are there in a gigabyte? I'm sorry? 1024, 1024. If the computer scientists understood Latin and Greek, how many megabytes would there be in a gigabyte? If they understood what a prefix was, 1,000, excellent. Why do computer scientists not understand?
Well, because it makes so much more sense to do that since computers work in binary, and so
Excellent.
it would be like a power of 2 is negative binary.
Excellent. So you anticipated the next slide. It's not that the computer scientists don't understand English. I will make no public statements on whether or not they do or do not. But they understand powers of 2 in mathematics. 2 to the 10, 1024, is almost 10 cubed. If it was exactly 10 cubed, every time we increase our n by 10, we would return to where we started, padded by 3 zeros. Because it's not, we have this small little thing which will eventually accumulate and eventually give us this Benfordness. Now, if you notice over here, this is moving up 10 more n and another 10n. You can see the leading digits don't change that much. It takes a while before you see the first 7 occur in powers of 10. Okay, so I mentioned some of my favorite numbers. Here are 3 more math favorite numbers, and there's some really nice pattern that's about to come, so please bear with me for a little bit. We'll have fun stories later. So gamma is the Euler-Mascheroni constant. Mathematicians are required to talk about it. It's wonderful. That's another talk. E, it's the base of the natural logarithms. Pi, circles. And so what we're doing is I'm looking at how close powers of these numbers are to Benford. And there's a great test in statistics called a chi-squared test. And the larger the value, the less likely it is that your explanation is correct. And so if your explanation is correct, 95% of the time, you should get a value of 15.5 or smaller. And if you look at these numbers, 2 out of the 3 seem to be doing a pretty good job. And even the third, it starts off bad, gets better, gets much better, then it decides to get bad again, and then it gets better again. So the question is, what's going on? Why is pi converging so much slower to Benford, and why is pi just all over the place, whereas E and gamma seem to be doing a much better job? So here's a nice plot. Because this is going so high all the way up to 46, rather than plotting the whole thing, I'm just taking a logarithm to just compress the vertical axis. So normally I give this talk in an audience of mathematicians. There's usually at least one super math geek who can rattle off digits of pi. Is there anybody here who can rattle off digits of pi? Yes? Nope, 26. All right, okay, good. All right, so good. So there's at least a certain minimum level of geekiness in this audience. Excellent. All right, we're now going for advanced status, and I think towards one of the prizes. Who can give me digits of pi squared? Yeah, there's a usual 9. What about pi cubed? Is it 27 or is it 28? Oh, yeah. So let's just look at this picture. It's nice sometimes to look at things when you don't know the answer ahead of time. Let's try to be forensic experts. You see something like this. Does anybody see any patterns? All right, so somebody in the back is going, one's going up and down. Okay, good. Yes?
In the red one,
Yes, the red one.
it goes on a smooth peak, and then a very steep and short, what do you call the water?
Trough.
Yeah, trough. And then it keeps doing that. And the distance between the peak and the trough slowly gets smaller.
Excellent. So the height of the peaks and the depths of the troughs seem to be decreasing. There is one other key item to notice here. Yes?
On the red line on the right-hand side, all of them have 2 little clips.
Okay.
Clips.
But there's something else about the red lines. That's unfortunately not the one I'm going for. How about how far I have to wait before I get the trough or the peak? About how big do you think this first one is over here? This is 0, 200, 400. Any thoughts about how big this first box is? I can't really zoom in on, well, I guess I could. No, doesn't work. Any guesses as to approximately how far I have to, somebody give me an upper bound for how far I have to go. 200, right? Clearly it's less than 200. Anybody want to guess? Here's 100 over here, 150, 50. Any thoughts as to what it should be? Yes?
I just had a question. Is this a chi-squared test of Benfordness?
It's a chi-squared test of Benfordness. And so what's happening is I'm looking at the first, here 200, the first 400, the first 600 powers of pi, and seeing how close those digits are to Benfordness. And what we're seeing is, for some choices of n, it's quite poor. For other choices of n, it's quite good. And the question is, what's going on here? So I really want to get a sense of how long the period is. So it's clearly more than 100, less than 200. Anybody want to wager a guess? Yes.
It's probably about 65.
About 165? Any other guesses? 180. So I'm hearing somewhere between 165 and 180. So I had asked about the geekiness of doing pi squared, pi cubed. If you were a super geek in your childhood, you might have gone up to pi to the 175, which is 1.0028 times 10 to the 87. What this means is every time I raise n by 175, it's almost as if I've padded my number with 87 zeros. Not quite. It's 1.0028. So if you remember what we had with the computer scientists with the powers of 2, we had 1024, 1.02. Now it's 1.0028. It's 10 times smaller in terms of that incremental change. And this is why the powers of pi take so long to converge to Benford. It's because of the algebraic structure of the number, because a power of pi is really close to a power of 10. Okay, so what I want to talk about now is a little bit about why Benford's law. So one of the biggest examples people use is the lengths of streets. And so is this going till 7, till 6:45? Till 7, okay. So it's looking at lengths of streets. So let's imagine you have a street labeled 1, 2, 3, 4, 5. Depending on how long the street is, you'll get different answers for the frequency of first digits. Let's say the last house on your street is 199. Then you've just gone through 100 houses that have a first digit of 1. And you'll have over 50% of the houses on this street have a leading digit of 1. If conversely, the last house is labeled 999, you've just gone through essentially 800 houses that have a first digit other than 1. So the probability of a first digit is going to fluctuate between 1/9 and 5/9, depending on how big your street is. And so here's a little plot. By now it should be clear, what is my favorite function to apply? The logarithm. And so if we apply the logarithm to the x-axis, to the street length, you can now see this periodic pattern of what's going on for my fluctuations for the length of the streets. I am from Boston. These streets are extremely strange there. They're all of different lengths. Some streets cross each other multiple times. I hate giving kudos to New York. I will say Manhattan as a grid is very nice, but for the purposes of this talk, a city like Boston is much better. It will give me a lot of streets of different lengths. And let's take all these streets of different lengths and let's look at the leading digits of people's houses. And so the first is I'm going to assume that there's 1,000 streets and every street is the same length. 1 to 10,000. So I'll assume I'm in some horrible place like Manhattan. And I look at the distribution of leading digits, and I'm actually doing the first digits and the first 2 digits, and I'm comparing that to the Benford probabilities. And not surprisingly, everything is equally likely because I stop right at a power of 10. So 1/9 of the time will be a first digit of 1, 1/9 of the time first digit of 2. Now, we're going to make it a little bit more complicated. I'm going to choose 1,000 streets again, but the length of each street is a random number from 1 to 10,000. And when I do this level of randomness, it's not Benford, but it's a lot closer. Well, if I do it once, I can do it twice. I do random, 10,000. I can do it again, random, 10,000. And you now see beautiful fits between Benford and the actual street data. And what's really going on in the world is the more randomness you have, the more likely you are to be close to Benford's law. And this is why it can be used by the IRS in so many different places. Okay, so I'm going to skip the stuff on the central limit theorem. It's there if anybody wants to. I want to go to applications now. Okay, this is the fun talk. Okay, so hopefully you can determine which one is me. This is the reason why I actually had to wear this shirt as a little subtle clue. I did not bring Cookie Monster with me. That's for a different talk. It is also related to tax fraud. Anybody know who the other Steve Miller is? No, but he is a great musician, and he is now in the Hall of Fame. The Rock and Roll Hall of Fame, not the baseball one. This is not the musician Steve Miller. Anybody know who this Steve Miller is? Yes, well, actually, former head of the IRS. So if you remember the IRS Gate scandal, where it turned out that certain IRS officers were told to delay processing requests for tax-exempt status to organizations that had certain key words in their title. They were using political words to influence policy. You should always do it mathematically, not politically. And they actually found that when they changed the names of these organizations and resubmitted it, they were processed much faster. And so eventually he lost his job at the IRS for this. So I want to be very careful now because this is being recorded, but a friend of mine says it is amazing what the Freedom of Information Act and a couple of $100 will give you. So this is from a couple of years ago. Somebody from Arkansas named William J. married to somebody named Hillary. It is amazing the data that is publicly available. Unfortunately, my friend who did this many years ago, and so the last data I have is from 1992. So I do not have any of the presidents since then, or future presidents. So when you look at something like this, like an individual, do you think people cheat on their taxes? Let me ask a different question. Do you cheat on your taxes? No, of course not. So this is like asking, are you a racist? No. So the question you ask is, what percent of your neighbors do you think are racist? What percent of your friends at your table, or maybe at your table is not a good way to do it. What percent of people do you think cheat on their taxes? 70%, that low. I'm sorry, that high? What category do you think people cheat on? Deductions. It's a little scary who is yelling this out so quickly. Why do you think people cheat on deductions? Well, okay, I will not go there. The IRS has now gotten a little bit better and asked people to provide additional documentation on charitable deductions. And this is often very painful. I have no idea how much the clothes I donated to Goodwill are worth. I don't know, I'll make up a number. What's a reasonable number to make? And people will make up numbers with certain properties. One of the properties is, what's the largest number I can put down and get away with? That's a really good property when you're making up numbers. Is there anybody here who has a corporate expense account? Damn, all right, I guess I'm on my own for dinner tonight. Okay. A lot of people with corporate expense accounts, unlike Williams College, are allowed to not submit receipts if the cost of the meal is below a certain critical threshold. A lot of times it's $25 for lunch. Anybody know what approximately the most common price of an executive's lunch is at such a company? Yeah, I'm hearing a lot of numbers around 23, 24. You don't want to push it too close to the threshold. 23.98, that's a good number. 24.15. And so there are certain categories where we are pretty sure fraud is going on. Whether or not a specific individual has committed fraud, that we don't know. We don't have enough data on something like that. But when we look at the aggregate distribution over the population, we are quite confident something is going on. Okay, so I'm going to talk about a bank fraud. So an audit of a bank revealed a huge spike of numbers, starting with a specific digit. Now when I say a huge spike, what number should have the biggest spike as a leading digit? 1. So what we're doing is we're looking at spikes relative to Benford's law. Okay? So there was one digit that was occurring a lot more than it should have according to Benford's law. Anybody have an idea of what digit that was? Not 9. 5 is close. Nope, not 3. 4, excellent, 4. A lot of them were 4s. It's actually good that people are not getting this too quickly. I'm a little bit worried after the charitable deductions. All right, and so they decided to investigate a little bit further. And they found that a lot of these numbers that began with a 4, when they looked at the second digit, one of the numbers or two of the numbers occurred more frequently than expected. Any thoughts? 8 and 9. Oh, I'm a little worried. I'm glad I didn't see who said that. And most of it was due to one person. All right, so I need audience participation. Do you have a credit card? Okay, I need a credit card right now. I do. It's really easy. Oh, yeah, that's fine. Mount Holyoke is fine. Although I might still be in their system, so thank you. Okay. So imagine you lose your credit card, or even worse, Mount Holyoke's credit card. What should our host do? Other than ask for it back from me, that's not on the table. Cancel it. So imagine you're the credit card company and someone calls up, maybe hysterical, maybe not, and they say, my credit card has been stolen. Oh, we're so sorry to hear that. Don't worry, you're not liable for the charges. Now, you're the credit card company. Do you investigate the charges that are outstanding? No. Why not? You expense it. It's too expensive. How many of you are Seinfeld fans? All right, there's a great episode with Kramer talking to Jerry about just writing it off with the VCR. And so a lot of expenses, it's cheaper to just write it off. The hassle of investigating it. So, I'm not going to publicly admit that I'm going to take this and buy myself like a $15 dinner. But let's say I did that. Is it worth Mount Holyoke tracking me down for $15? No. Let's say I decide that, my car is a little bit old and I want to buy a sports car to drive back to Williamstown in style. And so I put a $60,000 charge on the credit card. What about now? Yes. Still no? Oh, wow. I should have asked you instead of... So I'll just put this over here. So it's over there now. You may want to pick that up quickly in case there's somebody fast in the audience. Okay, so what do you think for banks the critical threshold is about whether or not they should investigate? $250,000. We've got some evidence here on the board. $50,000. No. $50. They're not going to investigate $50. The amount of time to investigate a $50, it would cost more for $50. 500 is close, 5,000. So a lot of places have a $5,000 rule. If it's above $5,000, it must be investigated. If it's below $5,000, you can just write it off. And what was going on is you had a worker at this company who had his friends sign up for credit cards. And they would run up debts of almost $5,000 just below the threshold. And then they would call, oh, your credit card's been oh, I'm so sorry to hear that. Don't worry, I'm going to fix everything for you. And he was doing it just below the radar. The mistake was he did it too many times. And then the pattern became noticeable. So I'm not advocating, but if you are going to do something like this, so what should he have done? Yes?
He should have spread them out and not have had them all right below.
Excellent. He should have spread them all out. What should the bank have done? Randomly pick amounts. So the bank should have been maybe anything 5,000 and over, we will investigate 100% of the time. And maybe 50% of the time, we'll investigate things from 4,000. This, the corollary of this for Homeland Security is every now and then, the old grandmother in the wheelchair has to be investigated in great detail by Homeland Security so that there is no category that is completely protected. You have to have people aware that no matter what it is, there's a chance that this could be investigated further. And so because the bank had a system in place where certain things were not going to be investigated, this allowed people to concentrate resources nefariously. There's lots of other places you can look at for Benford's law. One of my favorite is looking at hydrology data. This is looking at stream flow statistics for the past 130 years. I don't really care that much about stream flow, but the fact that it expands over a century and we have almost 500,000 records just made it a wonderful data set to look at. I'm not going to go too much into voter fraud, but there are numerous questions about Iran's elections in 2009. There are some instances in America where we know voter fraud has occurred. When you have more votes than registered voters, that's a clue. But what if you don't have more votes than registered voters? Benford's law is used in a lot of districts to determine whether or not it's likely. Sometimes rather than looking at the first digits, you look at the last digit or the last two digits. How often should the last two digits be the same? About 1/10 of the time. And so when people are making up data, people often have certain tendencies. And that's the whole idea of something like this. If I were to ask you to randomly flip 1,000,000 coins, assuming you have the patience to do this, you'd probably have about 500,000 heads. How much should the fluctuation be around 500,000? Those of you who have taken some math might know the central limit theorem, and you might have some sense of how much. What should the longest run of consecutive heads be? Right now the Sox have won 11 games in a row. This is great as a Sox fan. Should you be suspicious? If you saw Dustin Pedroia's dance last night in his audition for Dancing on the Stars, was that the right call? Or how many people heard about the Red Sox game last night? At one point, Red Sox pitchers struck out 11 batters in a row, which I believe is a new Major League record. Do you think the Red Sox pitchers are that good? Or maybe the umpire is being a little bit generous with the strike zone that night? Yeah. Yeah, I mean, it seemed like the strike zone had grown leaps and bounds over what it normally is. Sometimes it's a clue when the umpire calls it a strike before it's thrown. No, that did not happen last night, but as an interesting aside, anybody ever see the game show Whammy or its original precursor, Press Your Luck? You have a big board with money and prizes, and you have a lit square that goes around, and you go, big bucks, big bucks, big bucks, stop, and you have to look very excited as you're doing this. And there was an episode from the early 80s that they refused to air for decades. And what happened was, this is in the era of VCR, he recorded a bunch of episodes, and he noticed that the light was not moving randomly, and that there was a pattern. And you can actually see him smiling before it stops, because he knows where it's going. So he had figured out the pattern. So I was talking about analyzing round-off errors, determining optimal ways. These were the computer science. The tax fraud and image fraud. This is one of the great applications of Benford's law. So we've already talked a little bit about how it could be used in banks. Let me talk a little bit about... So right here. So here is a beautiful picture of trees. Probably a few months from now, this is what our area will look like. There is a cat hidden in the picture. Does anybody see the cat? Yes? The eye is probably in the tops of the trees? So how big is the cat? Pretty big. How big is pretty big? Like a quarter of the image, half the image, all the image? 2/3. There's the cat. You can write every pixel, every little dot here, as a triple of red, green, and blue. And typically we write them as numbers from 0 to 255. Computers like base 2. 255 is 1 less than 256, a nice power of 2. So instead of writing a number like 2016, which is base 10, 2 times 1,000 plus 0 times 100 plus 1 times 10 plus 6 times 1, you can write your pixels, your red, green, blue numbers, in base 2. And what people can do is they just change the last few digits. So if you had $2,016 in the bank and I changed the last digit to, now you have 2011, are you going to really notice that? Or is your bank account going to look approximately the same? It's going to look approximately the same. What people can do is they can change the last few digits of your image, your last few pixel digits of the red, the green, and the blue. And it's not going to change the image that much, but you can embed a low-res image in a higher resolution image. And then you just rescale that upward. So this is a great way to see different people can leave images on the internet with instructions on what to do. And they can publicly post it. They don't have to worry about transmitting secure emails. So the question is, can you detect if an image has been modified? So one possible applications of stuff like Benford's law is to stuff like that. I want to end with just one strange application. So it's the 3x plus 1 problem. Has anybody heard of the 3x plus 1 problem? It's the Collatz conjecture. Excellent. You should always end with something that will have people just up at night. So my two favorite quotes about this is Kakutani said, I would travel around the world and I would describe this, and people say, oh yeah, it's not that bad, and they would work on it, and after a month they would give up in frustration, and eventually people started saying it was a Soviet conspiracy to slow down American mathematics. The other quote is from Paul Erdős, who said mathematics is not yet ready for problems like this. This is one of the easiest problems to state. So I'm going to define a map as follows. It's going to be a map on integers, and if my integer is odd, I multiply by 3 and I add 1, and if it's even, I divide by 2. All right? So I'm going to start off with the number 7. 7 is odd last time I checked, so I multiply by 3 and I add 1, and I get to 22, then to 11, then to 34, Big Papi's number, 17, 52, 26, 13, how long do I have till 7 o'clock? Okay. 40, 20, 10, 5, 16, 8, 4, 2, 1. And now what happens? What do we go to? Now we cycle 4, 2, 1. 1 is odd, so we multiply 3 by add 1, we get to 4. 4 is even, so we go to 2, to 1, and now it just cycles on and on and on. So I'm not an economist, but some of my best friends are. This is more than enough data to make a conjecture. We have one data point. Anybody brave enough to make a conjecture as to what happens no matter what integer I start with? 4, 2, 1. So this is the famous 3x plus 1 conjecture. No matter what number you start with, eventually you hit 1, and you will cycle 4, 2, 1 for all eternity. It turns out that this is connected to an enormous amount of deep and powerful mathematics. And what I love about this is this can be described very easily. So why do you think I'm talking about it tonight? Yeah, so it's probably related to Benford's law. And so if you look at the distribution of the leading digits, so I chose a random 10,000 digit number. It took 241,344 iterations before it went down to 1. My computer had no problem with that. And we actually have ways to predict how many iterations it should be. And look, 30.2% of the time we observed a first digit of 1. All the way down to about 4.6% of the time a first digit of 9. So this Benfordness is in a huge number of things all over the place. And so what I hope you got out of this is that the mathematics we need to investigate stuff like this, a lot of it, it's basic arithmetic. It's the logarithm function. Some elementary statistics. And this is enough to flag interesting behavior. The reason that it occurs in so many different phenomena, that requires a little bit more work. If you've heard of the central limit theorem, it's very similar to something like that. But essentially, the more mixing you have going on, what happens is on a log scale, the more uniform you become. And anything that's Benford, it's uniform or it's even on a log scale. And then, of course, the big question whenever you do mathematics is, what use is this? I also do sabermetrics. It's not really hard for me to talk to audiences as to why you might want to do baseball analysis. What I love about this is I've been able to give a talk at the IRS headquarters in Boston. And so, in fact, when I went there, they gave me a nice parting gift. So I actually have an Al Capone bobblehead. So Al Capone, I think it's safe to say, was a very bad man. What did he do that was so wrong? Tax fraud. It's fine to kill people. We understand these things happen. But not paying your taxes? This is un-American. And that's what they took him down for, was for tax fraud. And what I love is I actually gave a version of this talk at Duke recently, and when I was traveling back, the Al Capone bobblehead set off the security system. And so you have all these Homeland Security agents who are actually frisking the Al Capone bobblehead. If I myself hadn't set off security, I would have taken pictures of that, but my phone had been confiscated at that point in the day. But anyways, I hope you got a sense of how the mathematics can be applied and what you can do with this. So thank you. Yes.
I have a question about the election applications.
Yes.
Many of us who are a little bit older remember the 2004 elections, and we remember that in the state of Ohio, the person who was in charge of the elections was a large contributor to President Bush, who promised Bush that he would deliver Ohio for him. And this was also the first election where voting machines were has anybody applied this?
So the person. So the person to look up is Walter Mebane. He's at the University of Michigan. I don't know of the analysis in the 2004, but from what I've heard of voting machines, I am very concerned about how voting machines record results. And I've heard stories of both sides of tampering with machines and how easy it is to change what they are recording. Anybody know Joseph Stalin's favorite or famous quote about voting? What matters is not who votes, but who counts the votes. And so the scary thing is when you have all this technology, how do you know it's recording the stuff properly? I do not know, the truth of what has happened, but from what I have seen on both sides, I am very concerned about results being recorded correctly.
If the data are contained in a single log, the first digit is going to be uniform, presumably. It takes a few logs of a data set for Benford's law to take effect, doesn't it?
So for a lot of data sets, we want it to be traveling over several orders of magnitude. And so, going into a little bit more of technical detail. Do people want more technical detail or just like hand waving? Hand waving? Or if you want, I can do technical detail afterwards. It's not enough to travel several orders of magnitude. That's the Al Capone bomb. There we go. I'll move Al Capone off to the side. It's possible to be Benford in one order of magnitude. For a lot of things, the more orders of magnitude you travel, the more likely you are to be Benford, but that's not a guarantee. You can definitely have processes that are peaking at certain places. If you look at a lot of businesses, it's not surprising that they have certain critical thresholds. This bill is going to be a certain amount. There's a college I was affiliated at, I will not say which one, where we looked at all the transactions, and we found a huge spike with fives. And then we turned out there were a lot of expenses that were $50 and $500, and just in terms of how much people are paid for certain activities. So if you are compressed in a certain region and you only have certain possibilities, you would definitely expect things not to be Benford. The hope is that if you have lots of different processes going on at the same time, that it will average out. So when you look at something like a tax return for a major corporation, what you do is you look at all the inputted numbers, not all the derived numbers. So whenever you're doing these arithmetic operations, that's going to naturally smooth things. You look at the numbers that people are inputting. I have talked to accountants because this is being recorded. I will not say which ones. And I probably haven't talked to them, but I'm sure if I were to talk to them, what they would say is that they frequently do Benford's test on the numbers corporations give them. And if the test comes out to be far from Benford, they may ask the corporations, are you sure you gave me the right data? Was that enough subjunctives? Yes?
I have one other question. Does Benford's law have an equals win in terms of the last number of a string of numbers? Is one digit more likely to occur in the last number as well as the
Excellent question. And so there is a law for the last number. And what happens, not surprisingly, is the more digits you have, the more likely it is for that last digit to become uniform and to have all the numbers occurring equally likely. Yes?
Why does one comma? Is it because? Why does one comma?
Why does one come up so often? So here's a really nice way to think about why one comes up so often. Let's imagine we are controlling a really good mutual fund or investment portfolio, and the investment portfolio earns 2% interest a year, forever. In this climate, that's actually not bad anymore. All right? So let's think about how long you're going to spend with the first digit of 1. You start at 1, then you go to 1.02. And the next year, you're a little bit above 1.04, and you're spending a lot of time in the ones. And by the time you get up to the 9, it doesn't take you that long to get from 9 all the way up to 10, but it takes you a lot longer to go from 1 to 2. And so as you keep cycling like that, you're going to spend more and more time in the low numbers.
So basically, because the
So you've got to be very careful when you say linear, not linear. So things that are exponential, when you have this exponential growth, you would expect things to be Benford, so long as the base is different than a power of 10. So for instance, if I multiply my numbers by 10 every single time, I'm not going to get Benford. I'm going to just keep getting the same first digit every single time. If I look at powers of 2, and I look at the first digit of powers of 2 base 10, it's Benford. But if I look at powers of 2 base 2, it's really boring. The first digit is always a 1. If I look at first digit of 2's powers with base 4, that also would not be Benford. So you need some kind of irrationality connection. But the really nice explanation, and in fact in Benford's paper, he calls it a geometric explanation, this geometric growth. Now the reason I probably should say a few words as to why it's called Benford's law. It was not discovered by Benford, it was discovered by Simon Newcomb in the 1880s. Looking at old tables of logarithms, he noticed that certain pages were more worn than others from use. I actually have a slide rule tie clip. Most people do not have slide rules on them anymore. I'm very proud that I still have this. No one looks at slide rules or log tables anymore, but in the 1880s, if you're doing scientific computations, you would look things up like that. And he noticed that people were going to certain numbers more often than others. And this is where it began. And then nothing happened for 50 years. And then Frank Benford independently discovered this in the 1930s, and he wrote a good paper on this. And the reason it's now called Benford's law is he had the good fortune to publish next to a really good physics paper that everybody wanted to read. And so nowadays, if you want to read a paper, you just go to the you just go to the internet and you just punch in what you want and you just download it. And maybe you'll get an ad because they'll now try to have these personalized ads to get you to do various things. But they won't give you other similar content. Back then they had these things called books and journals. And you would actually have to have the physical journal in front of you. And so when people were going to this physics paper, they actually saw Benford's paper in the same journal. And a lot of physicists and similarly minded people saw this. And from that it then spread slowly, and the number of papers each year that's that's written about Benford's law is exponential, is Benford.
Have you ever looked at orbits within a chaotic dynamical system? Because they don't go evenly. They visit some neighborhoods more than others.
Right, so that's a good question. So the question was looking at orbits in a chaotic system, which will visit certain areas more frequently than others. So what would you be looking at? Distance to maybe a certain central point?
Or just if you just had all the numbers between 0 and 1, and then you looked how many times does it go from 0 to 0.1, how many times from 0.1 to 0.2, 0.2, 0.3.
Right.
You would think it was equally spread, but it isn't. So I'm just wondering if that ends up being Benford in some way.
It would depend on the structure of the number. You can definitely rig up numbers and dynamical systems that will not be Benford. And in one of the papers I did, I jerry-rigged an extremely strange function where when you iterate it, you would get non-Benford behavior. My brother's an engineer and he says, yes, Steve, that's wonderful, but this would never arise in the real world. So the question is, which phenomena do you study and how likely are those to behave something like this? So it might be interesting to look at some of the chaotic systems and maybe like the logistic model, something like that. And I would say that one would not be Benford, if memory serves.
So on a truly random process, this doesn't.
Well, it depends where the randomness is. So if you have a process whose logarithm is a Gaussian, a central limit theorem, a normal curve, a bell curve, if the logarithm is normal with growing variance, then the original process is Benford. So one of the ways I often prove this, and this is using a little bit more mathematics, is the central limit theorem says if you have a bunch of independent random variables that are nice, that's a technical math term we use when we don't want to go into details, if you sum a bunch of random variables, it converges to being normally distributed. And so what you often do is you subtract the appropriate mean, you divide by the standard deviation to rescale things, and it becomes the very special standard normal. But you can allow the mean to grow and you can allow the variance to grow. And so a lot of processes, the normal kicks in from the central limit theorem. There's a central limit theorem that often kicks in on the logarithmic side, I talked about amalgamating processes. If you have something that's a product of a bunch of different things, well, the way we understand the Benfordness of something is we take a log of them. The log of a product is the sum of the logs. So as soon as you have a sum of logs, the sum of the logs becomes normally distributed with a growing variance. And then I have, not coincidentally, a couple of slides on this. Okay, so what I'm doing here is I'm looking at a normal distribution, and I'm choosing the normal distribution to have mean 0 and variance 0.01. So what that means is it's really tight around 0. Most of the numbers are between negative 0.01 and 0.01, or maybe negative 0.02 and 0.02. Well, since I'm throwing away the integer part, negative 0.01 is the same as 0.99. And so if I plot, I see most of my probability is a little bit after 0 and a little bit before 0.9. And it's not uniform. But as I increase the variance, now the variance is 0.1. We can see it's not uniform, but it's not that far off. If I increase the variance to 0.5, at first it may look like there's a lot of fluctuation, but whenever somebody shows you a plot, you should always look at the axis and see how they're labeled. It's going from 0.99990 to 1.0001. So there's almost no fluctuation. And so what's happening is already with a normal with variance 0.5, it's almost uniform. And then when you exponentiate that, that will give you Benford. And this is one of the reasons for the prevalence of Benford, is it's really a central limit theorem lurking in the background. Was there another question in the back? Or yes?
When Benford published, did he suggest applications, or who was the first one to apply?
So one of the first people to apply it to tax fraud was Mark Negrini, which wasn't until 50 or 60 years later. So a lot of times you have these mathematical theorems that are just out there as interesting statements. And it takes somebody who says, hey, what could we use this for? And the idea of using this to detect tax fraud was a brilliant idea. Is when people are fabricating data sets, they have some rough idea of, if I'm flipping a coin, I want half heads, half tails. But more sophisticated stuff, a lot of people don't know. I do a lot of work in number theory. You can use the Riemann zeta function to either detect tax fraud or commit tax fraud, depending on your personal preference.
My question was related to that last point. It would be hard to detect. I'm sure there might be evidence that people are reverse engineering this, using it to fraud.
Yes. So a couple of years ago, I worked on a project with 2 students to detect reverse engineering. I think the movie was Deep Impact. There were 2 Armageddon-type movies coming out around the same time with asteroids coming to hit the Earth. Oh, no, I'm sorry. It was Armageddon, where I think one of the conditions the people had to save the planet was, we don't ever want to pay taxes again. Ever. And so I have actually worked with some students on a way to detect if data has been reverse engineered. I have given that to the IRS. I have enough publications in my life that I can live with 1 fewer and have a couple more friends at the IRS. And I will not go into greater detail.
I think that we can thank Steve again. And please come up and ask any lingering questions that you have. And when you think about going home and telling everyone what you just learned, and you realize it's